More numbers. 24 park rangers assisted in the mission on the mountain. It happened on the Liberty Ridge roof.
It began like a whisper beneath Mount Rainier's storied summit, a surge of tiny tremors echoing through the mountain's innermost chambers. The USGS did not upgrade the alert level, which remained steadfast at green, but the seismic media buzz hinted at something far more dramatic: a red alert, born from mysterious rumors swirling among civilians and sensational sources. In reality, what unfolded was a record-setting swarm of micro-earthquakes, a geological chorus too persistent and too intense to ignore, calling for attention, not alarm. Before we start, please don't forget to like and subscribe to our channel for more updates. Starting the early hours of July 8, 2025, instruments detected one of the most extraordinary seismic swarms ever recorded at Mount Rainier. Hundreds, then over 1,000 small quakes rippled through the mountain's depths, far exceeding the usual annual dozen or so. Most occurred at depths of roughly 2 to 6 kilometers beneath the summit and clocked in at magnitudes far too low to be felt on the surface, none stronger than about 2.4. But the sheer volume was unprecedented. Despite the activity, the USGS Cascades Volcano Observatory and the Pacific Northwest Seismic Network firmly maintained that this did not signal imminent eruption. There were no signs of ground swelling, volcanic gas emissions, or unusual heat signatures, indicators that would suggest magma was on the move. Instead, scientists attributed the swarm to fluctuations in the hydrothermal plumbing system, hot water and steam shifting under pressure, subtly stressing faults and igniting tiny slippages deep underground. The media reported on the swarm in vivid detail. Over 1,200 quakes logged since July 8th, with some analysts studying around 780 of them as of mid-July. Still, experts emphasize that despite its record-breaking nature, the swarm remained within the bounds of benign volcanic behavior. It was energetic, yes, but not alarming. Even the USGS news releases carried a tone of measured reassurance. As of August 11th, about 1,340 events had been located. The strongest quake, a magnitude 2.4, occurred on July 11th. The swarm peaked at a staggering 41 located events per hour shortly after it began, before tapering back to 1 or 2 quakes per day by mid-August. These tremors, while unprecedented in number, remained harmless, silent in effect, not in origin. Scientists responded not with panic, but with curiosity. In Portland, a research geophysicist described the swarm on the radio. Over 1,100 located quakes in just a few weeks, compared to Rainier's average of 10 per month. She stressed that the largest quakes were still minuscule in scale, and none had been felt. The instruments, sensitive and precise, continued to record even the faintest tremors. Sometimes so faint they fell into the negative magnitude range. Hydrothermal fluids, not magma, were the main suspects. Warm water and gases shifting through the volcano's internal fractures, triggering seismic movements, rather than volcanic pressure building to an eruption. The lack of deformation or other signals suggested no magma intrusion. Conditions even appeared to improve gradually, with quake frequency declining over time. As the quake rate ebbed, a creative voice emerged to interpret the data through an entirely different lens. A geology professor at Central Washington University translated the seismic records into ambient piano music. Each earthquake became a note, its depth mapped to pitch, and its strength to volume. The result was an eerie, haunting composition, deeper notes for deeper quakes, louder keys for stronger ones. It was art, not analysis, but it allowed people to feel the mountain's tremors in a human way, reminding us that science can also inspire wonder through creativity. With no eruption in sight, the implications of this seismic saga were subtle but meaningful. It reaffirmed that Mount Rainier remains a dynamic, ever-evolving force of nature, not dormant but active in ways too slow and small for alarm, yet too persistent to ignore. The swarm served as a vivid reminder of the volcano's hydrothermal character, of water's unseen power to reshape Earth, and of the need for constant vigilance supported by dense monitoring systems. The episode also highlighted the USGS's strength in risk messaging. Amid speculative whispers and sensationalist headlines, scientists held the narrative steady. Green alert, normal, monitored, understood. Public access to data continued through PNSN platforms, and updates flowed via social media and official channels, even as recording devices captured hundreds of nearly invisible quakes each day. While not catastrophic, the swarm holds profound lessons for hazard awareness and preparedness. Mount Rainier is tagged as one of the most dangerous volcanoes in North America, not because it erupts often, but because of its vast glaciers and proximity to populated valleys. Layers of ice and ash rest above river basins where towns like Puyallup, Ording, and Kent sit, within reach of devastating lahars. As one analysis put it, a repeat of the ancient Osceola mudflow could obliterate entire communities and trigger tsunamis across Puget Sound. This seismic episode, while not eruptive, served as a reminder that the mechanisms of future risk, hydrothermal shifts, rock weakening, glacier melting, remain alive beneath the slopes. Instrumentation like acoustic flow monitors and lahar sirens, maintained and upgraded in collaboration with emergency managers, remain vital safety nets in this fragile landscape. Yet it's not just about hazards and warnings. The swarm revealed the subtle poetry in geology. That piano piece, born of tremors, reminded listeners that beneath the mountain's still white facade, movement persists. It transformed raw data into emotion, forging a bridge between the scientific and the spiritual, the analytical and the aesthetic. At its core, this story is one of humility. Mount Rainier is a colossus too slow to show its power in dramatic eruptions, yet too restless to ever truly slumber. It is shaped by forces both fiery and aqueous, sliding faults and shifting waters, observable only because we've placed sensors and attentively listened. The latest seismic swarm, the most powerful yet recorded, reminded us that vigilance is our responsibility, and that understanding this mountain's murmurs is not an option, but an obligation. The heightened attention around Mount Rainier's recent seismic activity has sparked a broader conversation about how we perceive volcanic risk in the modern age. Beyond the technicalities of hydrothermal systems and the precise measurements of seismographs lies a more human element: how communities respond emotionally to the mere suggestion that something unusual is stirring beneath a colossal mountain. Even without signs of magma movement or eruption, the idea of a volcano waking up resonates deeply in public consciousness. For many, the association with catastrophic possibilities overshadows the scientific reassurances, and that tension between perception and reality shapes how the story of Rainier unfolds. Mount Rainier commands a unique position in both the landscape and the imagination. Rising over 14,000 feet, its snow-capped peak dominates the horizon for miles in every direction. On clear days, it seems to float above the surrounding terrain, a serene and majestic presence. Yet beneath its glacial armor, it harbors the capacity for transformation on a scale difficult to grasp. Its very stillness is part of its mystique, lulling those who live in its shadow into a sense of permanence. But seismic swarms, even minor ones, interrupt that narrative. They remind everyone, from seasoned geologists to casual onlookers, that mountains are not static monuments but living systems, shaped by continuous processes invisible to the naked eye. One of the more intriguing aspects of Rainier's character is how its hazards differ from many volcanoes that have earned global notoriety. While its potential for explosive eruptions exists, the more immediate danger historically has been lahars, fast-moving torrents of mud, rock, and water generated when volcanic heat or seismic activity destabilizes ice and snow. Unlike lava flows, which tend to move slowly and can often be avoided, lahars behave like liquid concrete, racing down valleys at speeds that can reach 40 to 50 miles per hour. They can be triggered without any eruption at all, set off instead by landslides, earthquakes, or even the gradual weakening of ice walls over decades. This distinction is crucial in understanding why seismic swarms garner such interest. Any internal shifting, whether from magma or hydrothermal fluid, could influence the stability of the mountain's ice-laden slopes. Rainier's geological history reinforces the need for constant observation. Thousands of years ago, massive flank collapses sent debris flows that reshaped entire valleys. The Osceola mudflow, perhaps its most famous prehistoric event, buried parts of present-day lowlands under dozens of feet of volcanic material. Imagining such an event today is sobering, especially when one considers the growth of towns and cities in the region. The number of people living within potential lahar zones has increased dramatically in recent decades, and with them, the stakes of early detection and public communication have grown. The very act of monitoring Rainier is a sophisticated blend of technology and strategy. A network of seismometers, GPS stations, gas analyzers, and remote cameras works in concert to track the mountain's behavior. Seismometers pick up the faintest tremors, movements too small to be noticed by humans yet rich in information about subsurface processes. GPS units detect even the tiniest changes in slope or summit elevation, indicators that material might be shifting underground. Gas sensors sniff for changes in emissions, particularly sulfur dioxide and carbon dioxide, which can hint at magma moving closer to the surface. While all these systems reported normal conditions during the swarm, the very fact that they are in place allowed scientists to make that determination confidently and communicate it to the public with authority. The importance of interpretation cannot be overstated. Data by itself is inert. It takes trained experts to understand whether a spike in earthquake frequency is an anomaly or part of a larger trend. In the case of Rainier's recent swarm, volcanologists could compare the patterns to decades of historical data from the Cascades and beyond. This comparison is what allowed them to conclude that the quakes were most likely driven by fluid movement rather than magmatic intrusion. Without such context, raw numbers, over 1,000 quakes in a matter of weeks, could easily feed panic. Public trust in these interpretations depends on more than accuracy. It hinges on transparency. In times of unusual activity, agencies must walk a fine line between providing enough detail to satisfy curiosity and avoiding overly technical explanations that might confuse or alienate the general audience. At the same time, they must guard against downplaying risks in a way that could lead to complacency. This balance is part science, part communication strategy, and part psychology. Another dimension to the Rainier story is the cultural significance of the mountain. Long before seismographs dotted its slopes, indigenous peoples of the Pacific Northwest regarded the peak with reverence, weaving it into oral traditions and spiritual frameworks. To these communities, the mountain is not merely a geological feature, but an ancestor, a guardian, and sometimes a warning. Stories passed down for generations speak of times when the mountain shook or changed, interpreted not as random events, but as meaningful messages. While modern volcanology operates in the realm of empirical measurement, the cultural narratives remain an important layer of understanding, reminding scientists and residents alike that human connection to the mountain transcends instrumentation. Climate change adds another wrinkle to the equation. Rainier's glaciers, among the largest in the contiguous United States, have been retreating over the past century. This retreat alters the mountain's balance in subtle ways, removing weight from its slopes and changing the pathways of meltwater. Some researchers speculate that such changes could influence hydrothermal systems, potentially increasing the likelihood of small seismic swarms like the one recently observed. Though this remains an area of ongoing study, it underscores the interconnectedness of seemingly separate phenomena. Climate patterns, glacial health, and volcanic behavior are not isolated from one another. In discussing Rainier's hazards, it is also worth noting the role of emergency planning. While the recent swarm required no evacuations, it serves as a reminder for regional agencies to test and refine their preparedness protocols. Siren systems, lahar evacuation routes, and public drills are part of life for communities downstream from the volcano. Such measures might feel unnecessary during periods of calm, but when the mountain speaks, whether in whispers of microquakes or in louder signals, readiness becomes the most valuable resource. This recent episode also sparks reflection on the broader chain of volcanoes to which Rainier belongs. The Cascade Range is a product of the slow but relentless forces of plate tectonics, where the Juan de Fuca plate subducts beneath the North American plate. This geological arrangement is what feeds the magma chambers beneath many of the Pacific Northwest's most iconic peaks, from Mount St. Helens to Mount Shasta. Each volcano has its own personality, its own history of eruptions, seismicity, and hazards, but all are interconnected through the shared processes of subduction zone volcanism. Observations at Rainier, therefore, do not exist in a vacuum. They contribute to a larger understanding of the region's volcanic systems. Technological advances have expanded the ways scientists can see inside a volcano. Beyond traditional seismology and GPS, methods such as INSAR, interferometric synthetic aperture radar, allow for the detection of surface changes from space using satellite data to measure ground deformation down to millimeter precision. Other tools like muon tomography borrow techniques from particle physics to create three-dimensional images of a volcano's internal structure by tracking the movement of cosmic particles through rock. While not all these techniques are in regular use at Rainier, their growing availability promises deeper insights into the mountain's inner workings in the years ahead. The psychological impact of volcanic swarms on nearby populations is another topic of interest. For residents who commute daily with the mountain in view, seeing it on the news framed by words like swarm or alert can provoke a visceral reaction. Even when reassured by experts, the seed of worry can linger. This effect is magnified by the speed and reach of modern media, where initial headlines often outpace the slower, more measured explanations that follow. Social media, in particular, can amplify misinformation, making it harder for authoritative voices to maintain the narrative. Managing this cycle requires not only consistent updates but also creative approaches to public engagement, turning raw data into relatable stories or visualizations, much like the piano composition inspired by Rainier's quakes. On a more philosophical level, episodes like this remind us of the limitations of prediction. Science has made tremendous strides in monitoring and modeling volcanic systems, but the Earth still holds mysteries that defy easy answers. We can detect patterns, estimate probabilities, and outline potential scenarios, yet the exact timing of transformative events often remains elusive. This uncertainty can be unsettling, but it also fuels the scientific drive to learn more. Each swarm, each anomaly, becomes a data point in a vast and growing archive, one that will help future researchers refine their models, and perhaps one day predict volcanic behavior with greater precision. For the scientific community, the Rainier Swarm offers opportunities beyond immediate hazard assessment. It provides a natural laboratory for studying the mechanics of hydrothermal systems and their relationship to seismic activity. By analyzing the swarm's characteristics, such as the distribution of quake depths, the intervals between events, and the evolution of magnitudes over time, researchers can better understand how fluids move within the complex network of cracks and reservoirs beneath the volcano. This knowledge can be applied not only to Rainier, but to similar systems around the world, from the Andes to the Japanese archipelago. Educationally, the event serves as a teaching moment. Schools in the region often incorporate volcano science into their curricula, and a high-profile swarm offers fresh local examples to make the subject tangible. Students can track real-time seismic data, learn about the instruments used, and explore the connections between geology, geography, and community safety. In this way, the mountain becomes more than a backdrop. It becomes an active participant in shaping scientific curiosity and literacy. Even the tourism sector feels the ripple effects of unusual activity. Mount Rainier National Park attracts millions of visitors annually, drawn by its hiking trails, wildflower meadows, and panoramic vistas. While the recent swarm posed no danger to hikers or climbers, such news inevitably prompts questions from would-be visitors. Park authorities must be ready to field inquiries and, when necessary, adjust access or issue advisories. In the best cases, these interactions can enhance visitor awareness of the mountain's dynamic nature, turning a potential deterrent into an educational experience. As the days passed and the swarm began to taper, attention shifted from the immediate novelty of the event to its place within the broader geological narrative. Scientists will be sifting through the data for months, if not years, looking for subtle patterns that might have gone unnoticed in real time. This slow, deliberate analysis is where much of the true value lies. Beyond the headlines, beyond the momentary intrigue, in the gradual deepening of understanding about one of the Pacific Northwest's most formidable natural features. Rainier's latest swarm, in the end, is both a singular event and part of a continuum. It stands out for its intensity and frequency, yet it also fits within the long arc of the mountain's restless history. That duality, exceptional yet ordinary, is perhaps the most compelling aspect of volcanic science. It challenges us to hold two truths at once: that most swarms are harmless, and that beneath our feet lies the potential for profound change. Holding that tension with patience and respect is part of living alongside a volcano, part of what it means to share a landscape with a peak like Mount Rainier. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Mount Rainier's unusual activity, and what do you expect next? We want to hear from you. Thank you for watching, and see you next time.